session. Actually, Nigel has an announcement about the Lightning Talks session. So go ahead, Nigel.
Okay, so to prepare for the Lightning Talk session, for those who have not been at Real World Crypto before, you all have to queue up, and we're going to queue up by the stairs on stage left. And for those who are technically illiterate, that means you're right, okay? So stage left for the stairs to get, and there's be a queue. The amount of time you have to speak will depend on the length of the queue and whether I think your talk is boring or not. And there's no slides, no technical paraphernalia. You just speak until your time is up. Budget about 1 minute to 2 minutes for your talk, depending on the length of the queue, but usually average it's about 1 or 2 minutes. But we look forward to hearing your lightning talks at the end of this session on stage left. Thank you.
Okay, thank you, Nigel. Lightning talks are always a fun session, so please line up and give your lightning talk. All right, so welcome to the session on side channels and backdoors. We have 3 exciting talks, and the first talk is actually going to be given by Christina Garman and Daniel Genkin on failures in SGX. SGX has actually become kind of important in industry in trying to protect various secrets, and this talk, I think, is a very important one for people to keep in mind, in that SGX might not be as good as protecting secrets as we may have hoped. So Daniel and Christina, please take it away.
All right. Thanks, Dan, for the introduction. My name is Daniel Gemkin, and this is Christina Garman. And the title of our talk is SGX Fail, How Stuff Gets Extracted. And this is a big shout out to all of our collaborators from many places. And I won't read their names because otherwise we would simply run out of time. So let's quickly recap this idea of trusted execution environments. It is RWC after all, but I want to set some baseline. So it's a set of hardware features aimed to enforce data access control and isolation, integrity and confidentiality at the hardware level. So rather than using some crypto protocols to get these properties, instead we're going to rely on the CPU itself to guarantee that for us. And not only that, we would like to guarantee this in the presence of very strong adversaries, even if the operating system, the BIOS, the RAM, the hardware, everything around the enclave is corrupted, still code that lives inside the enclave can be safe because the security backing is by the CPU itself. Okay? And this gives us neo-native performance with strong security because we don't need to rely on heavy cryptographic machinery. The CPU just guarantees this for us. And when you stick this into DALI, well, you get this CPU wearing a chain for some reason. Okay? Now, there have been many instantiations of this idea, ARM Trust Zone or ARM CCA. Amazon has their Nitro Enclave, AMD has their SEV. But the topic of today's talk is perhaps the most well-known realization of this, which is Intel SGX. Now, SGX stands for Software Guard Extensions. It's a set of architectural features present in most x86 machines, starting from Skylake back in 2016, all the way to these days, now moving from client parts to server computers, coming soon to the cloud near you. Okay. Now, the nice thing about SGX is that it has an attestation mechanism that allows you to ascertain the genuinity of the hardware to which you're about to set your secrets. So if you're this remote client right there, and you're about to ship secrets into somebody's processor without knowing what that processor is or what machine is this over the network, you can still do this with attestation. It's cryptographically backed. You can make sure it's genuine Intel hardware and that you're talking to an enclave, and then it's safe to ship your secrets into the enclave. Now, because attestation is so critical to the trust of to trust in SGX, I'm going to spend another slide at how attestation flow actually works. So let's say we have some user enclave trying to prove that it's genuine and should be trustworthy. Well, it issues a thing called a quote, which is its own ID. This goes into the processor. The processor has an attestation key. It signs the quote. And then this quote is returned to the user enclave, now signed by the hardware, and goes all the way across the internet to a remote client. The remote client can't verify the quote by himself. Instead, he needs to go to Intel's attestation server to verify the quote for him. Intel knows what hardware they make. They know what keys are genuine and what keys are not, so they can verify this signature. And when the IAS says, yay, OK, then it comes back to the remote client. And only after verifying the IAS response, the client now feels safe to deliver top secret data into somebody else's enclave because they're sure that they're talking to a genuine Intel hardware and to a genuine enclave on that hardware and not some malicious simulator. So that's at least the idea. The problem with trusted execution environments is that they have enemies. And they have very powerful enemies in the form of side channel attacks. So what do I mean by that? Well, what happens once in a while is that these side channels attack the CPU, they extract the attestation key, and the trust of the entire attestation process actually depends on that attestation key. So when that attestation key ends up on Twitter, being used to sign various fun stuff, then there is a freak out, a responsible disclosure, and then very quickly Intel issues a microcode update that is being installed inside your machine's BIOS. And then every time you boot your machine, it updates the CPU and hopefully squashes all side channels. That's still not enough by itself because you need to rotate attestation keys, so let's do that. Okay? And now if you show up to the IAS with an out-of-date key, then you get an angrygram in the form of group out-of-date, which basically means, well, this microcode version is out of date, probably compromised, these keys are probably not trustworthy, we don't recommend you actually use them to put anything interesting here. So that's a quick view of SGX's attestation flow, and the takeaway that we found surprising as we did this project is how critical the BIOS is in actually enforcing the security of this thing, because every time there is an update following a logo then or a side channel, then guess what? You need to install fresh BIOS at your machine. The problem with BIOSes is that, well, installing them is a complicated manual process, requires experienced users. There's no automated way of doing it at scale. And BIOS vendors by themselves are very cautious because they're very careful about bricking motherboards. One mistake in a BIOS update and you're basically buying new hardware. So there's some inherent tension here, and when we decided to take a look at the BIOS release time between when the vulnerability became public and when the BIOS that actually fixes it becomes available, well, guess what? The picture is not pretty. It takes between 37 days and 329 days to even have that BIOS, yet alone now go and manually install this across your entire infrastructure. Okay? And if you're a vendor hoping to use SGX to hold your secrets, you're now in this dilemma because you can either allow unpatched machines and risk your secrets being exposed, or you can try making users to update their BIOS. The problem is that some users simply can't update, so you have to drop them. Otherwise are now pissed off because you have to guide them through this clunky mechanics of updating the BIOS. So then we found this awesome animation that basically outlines your problem. And what we'll see is that both approaches in this dilemma, no matter what you do, you're going to have issues. So the first case study we would like to talk about is Power DVD. And what is that? Well, 4K Blu-ray discs have DRM in them. They're encrypted, and you can't quite clone these discs. Now, the way that DRM discs, the way that Blu-ray discs are supposed to be played, they're supposed to be a hardware player, a big box in which you stick them into. But you might decide for some reason that you want to play them on your computer, and you can't quite do that except if you use one piece of software called Power DVD, which is the only software, as far as we know, that is licensed to play Blu-ray discs. What does it do? It spins up an SGX enclave and decrypts the disk inside the enclave using a protocol called AACS 2.0. Well, the thing is that they have a large user base, a very diverse set of platforms, and most of the users are actually pretty non-technical, so BIOS updates are not a thing that they would like their users to do, so they trust group out-of-date machines, which means that I could whip out my old foreshadow code back from 2018 when I was standing there presenting this, and went like, all right, well, you can dump the enclave. We reversed engineer AACS 2.0 protocol. It's full of wonderful crypto that this audience would enjoy, so go dig in our paper. This is like modern DRM. We could extract disk decryption keys, which of course now solves the wonderful open problem of watching Blu-rays on your AMD and M1 machines, also on Linux, because Power DVD only works on Windows. So now that we've solved that problem, there is very little that can be done about it, because you cannot expect Power DVD to start enforcing SGX updates, because otherwise they'll lose their user base. It's not clear what the countermeasure is here. And I'm going to turn over to Christina to talk about our second use case, which is the secret network.
Awesome. So we saw an example there of something where the system had a hard time enforcing BIOS updates. We're going to look at it now, an instance that hits that second bullet point of a system that tries to keep up to date and enforce updates through the attestation service, but we still see issues in practice with this being utilized. So if you're not familiar, the secret network is the first production instance of TEE-based private smart contracts. If you're not familiar with what a smart contract is, it's basically a stateful program that users can interact with then that can make automated decisions regarding the transference of assets. So Secret launched their privacy-preserving smart contract features in 2020, and right now they have a current market cap of roughly over 100 million USD. At a high level, it basically works by storing the same private key in every validator's enclave. And this key and all the other associated material is derived from what they call the consensus seed. And this seed was generated at the start of the network, and it's given and provisioned to every validator that joins the network then. And crucially, all the transactions and contract state and on-chain data and all of this is encrypted to this key. And this is where we get the privacy-preserving features from. So how does this work in a little bit more detail? So let's say we have a validator enclave and you want to set up a new validator node. What do? So the first thing you do is you go through the attestation process that Daniel discussed, and to make sure that you are genuine Intel hardware and that you are actually fully patched and up to date, running the latest microcode and all of that. If this passes through the network and all the attestation checks out, then the network provisions you with the consensus seed, which allows you to derive this private key and everything else that you need. And as more validators come along, this entire process just keeps happening. And this allows them to then maintain the state, execute contracts in a privacy-preserving way. So if you're a user now and you want to execute a smart contract, what do? So you take whatever your transaction is, whatever your update is, whatever you want to do, you encrypt it, and you send it over to the validators where it's loaded into the enclave. Only then, once it's in the enclave, is it decrypted, because that's where all the keys and the secrets live. The update or whatever happens, and then everything that's sent onto the chain then is encrypted. And because all the validators share the same key, they can all access this information, allowing them to maintain the chain. So like I said, this started in roughly 2020. Secret had been running along, doing this system. And then in August of 2022, XAPIC was disclosed with a public assertion that patching wouldn't be enforced until March or April of 2023 by IAS. And so we'd already been working on this project, looking at Power DVD and things like this, but this got us thinking. So what can we do then? So we have this gap between disclosure and enforcement. Would we be able to get a validator node up and running then on the system that passes the IAS attestation process but is still vulnerable to APIC? And if we did, what might we be able to extract and what might the consequences be? So this is exactly then what we set out to do. So I want to note that this quote up here, this is from Secret's gray paper. It's important to note that the majority of theoretical attacks that occur on TEEs and SGX in particular happen within research labs. So we also set out to kind of, debunk this kind of widespread assumption that these attacks are purely academic in nature and don't actually impact real systems. So there's a lot to unpack here. We're not going to go through this too much, but setting up the validator node, which is the first thing we had to do, was actually one of the toughest parts of the attack, because setting us up SGX is actually harder than breaking it. But if you want to, learn more about this, please come talk to us. There's lots of fun little oopses and fun things that we had to talk about. But once we navigated all the hardware and figured out what CPU we wanted to use, we were able to successfully register a computer onto the network as a validator that was vulnerable to XAPIC, even though it passed through the attestation process. So once we have this, and one important thing to note is that any node that registers as a validator, even if it's not actively adding blocks to the system or contributing, is provisioned with this consensus seed. So the attack basically costs just the cost of a registration transaction, which is 1 secret, so less than $1 US. So once we have our node up and running, now we can extract the consensus seed, because we have a vulnerable node that we can attack. And once we have this consensus seed, the keys derived from the consensus seed then allow us to decrypt any transaction or contract state that exists. We actually wrote a fun little tool just for the testnet that we called Pcrypt, which allows you to take any contract state, any encrypted data on the chain, plug it in, and decrypt it, basically breaking all of the privacy guarantees of the smart contract system. We also built our own little private NFT that we loaded up onto the chain. So there is a fun little rubber ducky NFT hiding somewhere in the secret network if you want to go find it. So I do want to talk briefly about mitigations here because unlike with Power DVD, where there's really not a lot they can do, there were things both short-term and long-term that Secret both did and is working to do, and things that we recommend in terms of mitigations. So the immediate thing that they did is basically froze registration to block all new nodes, so other people couldn't come in and do exactly what we did and register vulnerable nodes onto the network and potentially steal secrets. They actually did this through an interesting mechanism. They didn't change the protocol or the code or anything like that. They basically just revoked their developer key with IAS, which meant that anytime you tried to go to IAS to ask for attestation verification, they just said, no, we don't want to talk to you. So if you couldn't pass attestation or couldn't even interact with the system, then no new nodes could register. So in the short term, then, what have they done? So they actually then, before TCB recovery happened, they implemented an allow list to make sure that only non-vulnerable processors could join. So this is actually done using a feature that we didn't talk about in the attestation process, which is that there's actually a group ID that is part of that process as well that goes into the report. And this basically bins processors into families. So what they could do then is check not only that your IAS passed, so you weren't vulnerable to like anything before XAPIC, but they could also then check your processor family to make sure that you would not be vulnerable to XAPIC as well. That way they could trickle in new nodes and still keep the system running. And then after TCB recovery, interestingly, they've also enforced that only server class hardware can actually join the network, obviously as long as their microcode is patched and up to date now. So in the long term, what are they doing, or what have we recommended? It actually turns out they didn't have any sort of strategy for rolling this consensus seed into place. I guess I don't know if they didn't expect to have to do this or not. So they're developing a strategy for figuring out how to roll this one consensus seed because of the fact that it could have potentially been extracted. Also, moving toward a more defense in-depth system, making sure there are many layers that you might have to dig through before you can get to secrets or keys, and also from a defense in-depth perspective, making sure that there's not necessarily just one secret that rules them all, where if you're able to extract it, you're able to break all of the privacy guarantees of the system. So I want to wrap up by talking a little bit more broadly about lessons learned, both through our disclosure process and as well as from this work. So from the disclosure process, we actually got to see firsthand that there's a constant tension between different SGX deployments. So some deployments need fast rollout of patches, TCB recovery and attestation reports, like the secret network, who needs IAS to be enforcing patching as soon as a vulnerability hits the public, so that way no one can register vulnerable nodes again like we did. But some larger scale systems or other deployments might need significant time to roll out updates. Maybe they have a large number of nodes that they need to install the updates on and BIOS updates and then reboot the entire system. Maybe there's reliability checks they need to do, et cetera. But the way that the system is set up right now with this single attestation server and service, it lumps everyone into the same boat where everyone has to run on exactly the same update timeline. We actually got to see this in practice with this XAPIC live. So when it first came out, you can see that they plan to enforce it in April of 2023. Then we came along and disclosed our work, and they were like, uh-oh, we better start enforcing this. So they picked November 15th as an enforcement date. And then they got pushback from some other deployments that said, no, 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 we can't be ready by then for you. We won't be patched, and our machines won't patch attestation. We need more time. And you watch them yo-yo then to the final date they settled on, which was November 29th. So you can see this tension really at work then between different deployments and what their needs are. In terms of broader, more generic lessons learned, again, if we go back to our theoretical attacks, these attacks are not just theoretical. Clearly, they have significant real-world impact. They're also not just done in research labs. They're done in grad students' apartments. But this is not just theoretical. It clearly can have significant real-world impact. In terms of what the users, for example, can learn, you should, if any, you use a system that has SGX somewhere in the pipeline, you really need to understand the impact on your data when SGX is broken. What data is used in there, how is it used, and what happens in the event of a compromise. For developers, you really need to plan ahead for TCB recovery, and you have to assume that SGX is going to break. You can't just plan and not have a strategy. You have to develop your system with strategies in mind for how you're going to go through this process. And it's also really important to understand what information might leak via different classes of attacks and what the mitigations are. There's not a lot of time for me, we're not talking about it here, but we actually, as part of this work, we've also built a comprehensive categorization of all the publicly known hardware attacks on SGX, the information they leak, what the various countermeasures are and stuff. So check that out if you're interested in learning a little bit more about that. And again, I want to emphasize that defense in depth is still important. Side channels are an active research area, as we all know, and you have to assume that SGX is going to break, and you have to plan for it. It breaks early, it breaks often, and once it stays broken, it's broken for a while. So you've got to plan for that. And we also did a lot of discussion about future TEE design recommendations. For example, that they really need to include a better mechanism for fast and automatic updates, because as we see in this BIOS update mechanism is not sustainable and doesn't necessarily work in practice. So with that, I want to thank you for listening. This is our website. I urge you to go check out everything. And I want to have a shout out and a thank you to all of our awesome collaborators on this paper. And with that, we will take questions.
Great. We have time for one question.
Maybe I shouldn't have been the one question, but if you wanted to make if somebody wanted to make an enclave that wasn't going to break, and they could do whatever they wanted, you know, FHE, crazy ceremonies, what would they do?
That's a very good question, and it very much depends on your use case. There's not going to be a one-size-fits-all here. It really is not clear what to do, and very much depends on your use case, on the computation you're trying to run, and what you're trying to do.
That sounds like a whole other lecture.
Yes.
Yeah.
Yes.
Okay, fine. We'll take one more question, and then we'll move on.
What stops you from tweeting the consensus seed?
Say again?
What is stopping you from tweeting the consensus seed?
From tweeting it?
Yes.
That would not be nice.
Great. Okay,
You also have to get a
talk.
broadcast to everyone else.
Thank you both. And yeah, let's thank the speakers one more time. And then okay, our next talk is going to be on randomness failures, and in particular, randomness in the Cisco ASA.
Hi. Sorry. Hi, I'm Riyad, and with my colleague Arnaud, we will present you some findings on randomness issues in Cisco ASA line of product and our responsible disclosure to Cisco about this. So the beginning of the story was when we were working on a cryptographic library on elliptic curves and X509 parser as internal projects. And we had to test them on a quite large set of certificates, over than 250 million certificates. And among them, we stumbled upon ECDSA certificates with duplicated nonces and duplicated keys. After further investigation, we found out that all these ECDSA certificates were self-signed certificates from the same vendor, Cisco ASA. More investigation showed that RSA self-signed certificates from the same vendors suffered from also modulus duplications. And as we can see here, the proportion of duplication is quite large. Focusing on ECDSA, one thing to notice is that nonce reuse on ECDSA is quite devastating, since using the same nonce with the same private key will break both the nonce and the private key. And we exploited this attack since we had some intersection between the duplicated nonce certificate set and the duplicated key certificate set, using a kind of iterative algorithm where we were bouncing from a found private key to a found nonce and vice versa. And we were able to break 5,000 certificates keys using this algorithm. Obviously, duplicated nonces and certificates tend to point at a serious RNG failure here. And in the state of the art, we have many topics on that. And we will briefly discuss some of them. In 2008, Debian OpenSSL patched library had some serious RNG failures that allowed to break SSH and SSL keys. In 2010, the PlayStation 3 of Sony used the same nonce for signing different signatures, and this allowed, with a nonce reuse, the compromission of the master firmware signing key. No random at all were used back then. In 2012, regarding RSA, prime factors were generated with collisions, and this allowed some GCD attacks recovering these prime factors. These attacks did not work on our set, and we will explain why later. And finally, in 2013, we had at the same nonce reuse attacks on crypto wallets. More interestingly, and regarding our precise topic on Cisco ASA, in 2019, there were CVE that was actually presented at RWC this year in 2019, and that was concerning low entropy keys. And interestingly, we stumbled upon this issue by surprise using our set. And we will show that the root causes of this was not fixed, and how we reported this to Cisco with the responsible disclosure, and hopefully fix this in a new CVE this year. So first of all, we have plotted here the proportion of broken keys in certificates in our set, showing that after the 2019 CVE, the proportion remained the same, showing that the root causes were not fixed back then. This forced us to try to understand what happens inside the appliances. And the ASA appliances actually are firewalls that implement VPN, IPsec, TLS, etc. And they come in two flavors. The first one are hardware appliances using cryptographic and network accelerators, and we got one for quite a cheap price. And we also have a family of virtual appliances, ASA-V, V for virtual, that do not make use of network and crypto accelerators, but they share the same firmware as the hardware appliances. In this talk, we won't detail the instrumentation of these appliances because we don't have time, but we will have a full-length article that will detail this. So regarding, first of all, the hardware appliances, since it is quite complex to instrument them, we only provide here a black box approach through scripting, showing that for various firmware versions that appeared also after the CVE, we exhibit some collisions on modulus, nonce, and keys, even for recent firmware. So that confirms also that the problem is still here. Now, we had to try to understand deeper what happens on these appliances. So we had to perform some analysis, and through our instrumentation of virtual appliances, we kind of came up with this separation in layers that will provide randomness generation in the appliances. And we have many primitives per layer, so we won't detail all of them, but we will only focus on the main ones. First of all, we have entropy sources and lifters. Among them, we have cheap sources that provide almost no entropy or only a few bits of entropy. For example, the unseeded round function will provide no entropy at all because its output is known. We also have get time of day at the microsecond resolution. We have another version in Cisco firmware that will provide 10 milliseconds resolution, which is a bad idea, as we will see later. We also have better sources in the firmware, like RDRAND and RDSeed, that are instructions that provide 64-bit entropy seeds. However, these sources really depend and rely on the underlying CPU and the options for virtualization in the hypervisor, so we cannot count on them everywhere. And these sources will feed entropy lifters, mainly LFSRs, LCGs, but using only 32-bit seeds usually. We also have a lifter from the RSA Labs BSafe library that is used inside the firmware, and we will explain this later. These entropy sources and lifters will feed deterministic engines. These engines are quietly separated in two families. The standardized ones, standardized by NIST, so a CTR, a counter mode DRBG is used with AES, and a hash DRBG is used with the SHA-2 function. These implement an instantiate, generate, and reseed API. We also have the ancestor of these deterministic generators, the MDRAND OpenSSL function that is based on the old SHA-1 PRG. But the key point here to keep in mind is that D stands for deterministic. These engines do not make miracle. They can't invent, they can't come up with new entropy. They are only as good as the entropy sources feeding them. Finally, we have the key generation layer. And in this layer, we have RSA key generation that we unveiled through our analysis. We have seen that seeded generation is used here. A 28-byte seed will generate the P and Q prime factors. And this perfectly explains why the GCD attacks don't work here, because when we have collisions on both P and Q factors. Regarding ECDSA key generation, we use the firmware uses a classical OpenSSL generation over the NIST prime curve, and it reduces it modulo the order, so nothing new here. And regarding the nonce, we have two paths for generation that we will explain later. We have the BSafe based part and a hash DRBG based path. And now I let Arnaud explain all this.
Thank you, Riyad. Riyad has presented all the building blocks that there are in the Cisco firmware, and we will now take a look at the boot process regarding the random part. So basically, all the firmware we take a look at have the same kind of pattern regarding the boot. They're all instantiate deterministic generator, being a CTR DRBG or MDRAND from entropy sources and lifters. And then the pattern is the following, where users, callers, will grab random, request random from the deterministic generator, 16 byte, 3 times 16 byte, 3 times 16 byte, and so on. And at some point, the RSA certificate will be generated. It's a cell-time certificate, so 28 bytes of random will be requested from the deterministic generator and will be given to the FIPS algorithm in order to produce the RSA key, and then the RSA certificate, the self-sign certificate, will be generated. After that RSA certificate, another certificate is generated, an ECDSA self-sign certificate. So for that purpose, an ECDSA key is generated by grabbing 32 bytes random from the generic the deterministic generator. And in order to produce the signature on the certificates, you need a nonce. And that nonce is not directly taken from the deterministic generator, but it's taken from the BSafe. So we request 32 bytes from the random from the BSafe, and that BSafe lifter has been initialized with 24 bytes of random, 16 bytes, and then 8 bytes. So there is already a problem in there, 24 bytes in and 32 out. There is another variant for the generation of the ECDSA nonce, which is used for the signature of the self-sign certificates, where we use an HDRBG instead of the BSafe lifter. It's initialized from entropy sources. One word on the BeSafe lifter. It's basically a construction made on SHA-1 and reduction modulo, let's say small prime, 160 bits. What can be said on that is that it's cumbersome but deterministic. So once you have understood how it works, you can reduce the block and just consider it as another lifter. Let's now take a look at the specific version in order to explain how we worked with Riyad in order to understand the root cause of the issue. So we took the version 9.10.1 because it's probably one of the most interesting one. The idea we had is to, in order to understand and validate our understanding of the issue on the ASA-V and on Cisco globally, we decided to implement some kind of Keygen or proof of concept where the idea was to be able to construct or reconstruct all the private keys that were associated with the certificate, with the broken certificates. So we will present how we did that in order to have a valid input to provide to Cisco for the advisory. On this version, the mechanisms that are used are a CTR DRBG. This is the main deterministic generator for RSA-seed and ECDSA key. The ECDSA nonce is requested to be safe, which is seeded from the CTR DRBG. The interesting part is the instantiate, where there are two main parts. The personalization string is almost fixed, with only the time from boot rounded to 10 milliseconds being used to provide variability. And the most important part in DRBG instantiation should be the entropy nonce, which is provided during the instantiation. In that specific case, you have 40 bytes and 20 bytes of random, which are taken, or so-called random, which are taken from MD round, which is itself instantiated from a seed from an LFSR, which is itself seeded from 32 bits of RDTSC. So at the end of the day, in this version, you have only 32 bits at the roots of the DRBG. Another interesting part with this version is that when you call the generates to get random from the DRBG, in the various calls for creating the keys and stuff like that, you have function where you can provide additional inputs. And in that specific case, the additional input function uses the time at the moment of the call rounded to 10 milliseconds. And when you want to do a Keygen in order to emulate that, you have to take that into account. So the question is, what's the complexity of finding all the private keys for the certificates which are generated by this version? Basically, you have two parts. You have 32 bits of seeds for seeding the LFSR, and something like 13 bits of time complexity, which is associated with the rounded time value that you inject each time you call the generate. So the complexity is like 45 bits with a large constant because there are at every point EV-DRBG calls. So the idea we have to validate our implementation, because there are various elements to take into account, is to do a meet-in-the-middle solution. We decided to remove the LFSR seeds part by modifying the binary ASA-V firmware that we had with a non-fixed seed and work on the second part that was more on the CTR DRBG to validate that our code did work and understand how if we had problem with that. So what you see here on the picture is the timing value which are provided at each generate call. So what you have here, it's quite a large amount of volatility for the first value, which is the boot time during the instantiation, and we see that every time the firmware boot, we have the same pattern, and the pattern shows that between the different call to the generates, we do not have a large variation between the time value that are passed to the generate. So we are in a good position to emulate that and to reduce the complexity. What we did is that we considered the average curve and a small envelope around that in order to work to validate our proof of concept on a small subset of all the keys and keys that would be all the private keys that would be associated with broken certificates, and to validate that our code did work on that. We did that on an unpatched version, and on the patch version, and then on an unpatched version by verifying that we were able, for this small part, to get back to the private keys associated with the certificates that were generated. So in 8 days, we have quite good confidence that we had a valid key agent for this version. Now that we have presented what we did on this version, we also did the same kind of stuff on all other versions that are in this table. And this table summarizes the result we have for all this version. So I will not take all the lines and columns of the table. What's interesting is that for all this version, you have broken RSA modulus, nonces, and key, and we are able to provide keygen for most or all of these elements for some versions. The other interesting part is the last column, which shows the complexity of providing keygen for those versions, which is say 32 bits most of the time. There is even a version for which there is a 16-bit complexity keygen for this version. And the last point in this slide is the word seeded that you see everywhere on the command column. What it shows is that in most Cisco ASA firmware construction, you have stacks of lifters, one on top of the other. So for instance, if you take the version, the 9.6.4 version, the main DRBG is a CTR DRBG, which is seeded by MDRON, which is itself seeded by a HDRBG, which is itself seeded by a LFSR, which is itself seeded by 32 bits of RDTSC. So you have a stack of stuff, but no entropy at the root of this stack. So at the end of the day, it's bad. So as a conclusion, we hope you enjoyed following the White Rabbit with us on this journey, which started with duplicated nonce and keys in certificates, and for which we had to do keygens and implement stuff in order to understand how things work, in order to report that to Cisco and help them fix their code. We learned some stuff during that journey. I mean, learn is not quite the word. It's probably something we already knew, but which should be repeated to other developers, is that when you work with random in your firmware, you have to consider the following. You have to fail instead of having a fallback to a bad entropy source. It's better not to use rand and say, okay, I can't provide entropy, and not having a fallback to run. When you are auditing such code, you should consider the worst code paths regarding the random providers and remove them if they are not acceptable. One thing which would help is mixing multiple sources instead of using a single one. And there are some DRBG takeaway messages where DRBG, as Riyad explained, are deterministic. So they are good, but you need to have random at their root if you want to be somewhere at the end of the day. You need to have good add-ins, and reseeding is a requirement, but it's almost never used, so it should be. Some final thoughts. The beginning of the story was a black box approach where we saw bad certificates, but in fact it's not sufficient. Sometimes in one of the version or two of the version we had good looking keys for which we thought there was no problem in those keys, but at the end of the day we were able to do a keygen for that key, for that set of keys for this version. Because for instance, if you don't have enough samples, you won't hit a birthday paradox, and so you won't be able to see that there is a problem in the keys, and you will think it's okay, and in fact it's not. The other element is that it's not because you have good DRBG or PRNG, or even if you stack them, that you will end up with good random. You need entropy at the root of that. And if you are interested by this presentation and you want to learn more about the instrumentation work we did, there will be a full-length article that will be presented at STIC conference in a few weeks. If you have questions.
Great, thank you for the wonderful talk. We're a little bit behind schedule, so maybe I'll ask for questions to go offline. So please find the speakers to ask any questions.
Thanks.
Looks like terrific work, so thank you very much. And let's see, the last talk of the session is going to be on actually related to the suit of the PRGs we saw in the standard we saw in the previous talk about breaking basically breaking the Macaulay-Schnorr generator. So yeah, Ken and Adam, floor is yours.
All right, thank you. So welcome to our talk on the possibility of a backdoor in the Macaulay-Schnorr generator. I'm Keegan Ryan. I'm co-presenting with Adam Sewell. So in this talk, we want to present you with a cryptographic mystery that has been puzzling researchers for the last 10 years. And although this mystery still remains unsolved, we've recently made some breakthroughs and we have made some good progress on this problem. And that's what we want to present to you today. And it's entirely possible that one of you in the audience has the missing piece that can answer this question once and for all. So this story begins with a random number generator that you may already be familiar with, dual-EC DRBG. So dual-EC was first proposed for standardization in a 2004 presentation at a NIST workshop. Now, I apologize for the confusing diagram. This was taken from those 2004 slides. The important thing is that dual-EC is based on asymmetric cryptography, specifically elliptic curves. Dual-EC was eventually standardized in NIST Special Publication 800-90A. And as part of the publication, it included multiple pre-generated pairs of elliptic curve points, P and Q, to be used by default in the RNG. Throughout the standardization process, dual-EC was the subject of a lot of cryptanalysis, and multiple groups independently came to the conclusion that it would be possible to backdoor dual-EC. In essence, if you know the discrete log of the elliptic curve points P and Q, you can observe some of the output of dual-EC, recover the secret internal state, and then use that to predict all future outputs. Now, in spite of this weakness in dual-EC, it remained in the standard. Multiple companies began to implement dual-EC, and this included a company known as Juniper Networks. Now, in 2012, Juniper Networks was hacked, and their values of P and Q for dual-EC were replaced with different values. So this replacement would allow this adversary to passively decrypt the VPN communication going through these Juniper Networks devices. This stayed in place for 3 years until it was finally patched. And we say this as a way of motivating that even the potential for a backdoor can have catastrophic security implications. So we're skipping over a lot of the details in the history of dual-EC, but why are we talking about it anyway? This talk is about Macaulay-Schnorr. So Macaulay-Schnorr was first proposed for standardization in a 2004 presentation at a NIST workshop. I apologize for the confusing picture. This is straight from that 2004 slide deck. The important thing to take away here is that Macaulay-Schnorr is based on asymmetric cryptography, specifically RSA. In spite of the poor performance, Macaulay-Schnorr was ultimately standardized in ISO 18031, and as part of the standard, it includes these pre-generated RSA moduli. And think about that. Why would a standard need to include a pre-generated RSA modulus? What happens if you know the factorization? So it seems the similarities between dual-EC and Macaulay-Schnorr end there. There's not an obvious way to use this knowledge of the factorization to recover any sort of information about Macaulay-Schnorr, so it seems, at least not in an obvious way. But on the other hand, there were subtle changes between the version of Macaulay-Schnorr that was initially proposed and the version that was ultimately standardized, specifically to increase the output length. And the proof of security for Macaulay-Schnorr depends exponentially on the output length. So this change seemingly has the effect of totally invalidating the proof of security. What is going on with Macaulay-Schnorr? Well, Macaulay-Schnorr is pretty simple and easy to describe. So the internal state of Macaulay-Schnorr is a large integer s. We take s and we raise it to the power of e modulo n. So we essentially perform a textbook RSA encryption with e and n, where those are the default values from the standard. We can then take the k least significant bits and output those as the RNG output. And we take the remaining most significant bits, and that becomes the new state. So this gives us a very nice algebraic relationship between both the states and the output. If we need more than k bits of output, we can repeat this process again and again until we have enough output. So if you're familiar with the Blum-Blum-Shub generator, you might recognize this as being similar. In the case of Blum-Blum-Shub, there's one or just a few bits output at a time, but in the case of Macaulay-Schnorr, there can be thousands of bits output at a time. So this leads to the very natural question, does all of this additional output give us some advantage in recovering the state or breaking the RNG? And the very natural thing to consider here is that since the outputs are based on RSA encryption, what happens if we go backwards? What if we use knowledge of the factorization to perform RSA decryption? And it turns out that this doesn't seem to make the problem any easier. Because we're only outputting a subset of the bits, we only know partial RSA ciphertext. So it's unclear how we reverse this process to get back to the original state. So there's not really an obvious way to backdoor Macaulay-Schnorr, and even doing some small amount of brute force, like was done in the case of Joule-EC, doesn't seem to help here. And that leads us to the main question of this talk. Does knowledge of the factorization of these hard-coded public moduli lead to some sort of attack on Macaulay-Schnorr? And we want to open this up to be even more general. You don't have to necessarily know the factorization, but any sort of malicious construction of these public moduli. And this question is still unanswered. We don't have an answer to this question. But what we do have is a number of interesting observations about Macaulay-Schnorr. And the first observation is that there aren't any simple backdoors in Macaulay-Schnorr. So to be a bit more precise, by a simple backdoor, we mean that there are no backdoors that rely exclusively on RSA decryption. The way that we show this is we take the construction of Macaulay-Schnorr and we replace RSA encryption with a random invertible function, more specifically a efficiently invertible pseudo-random permutation. Now you can think of this as similar to a cryptographic sponge in duplex mode, and we can show that this modified construction is secure. So that tells us that if the standardized version of Macaulay-Schnorr is not secure, then that's because the RSA encryption does not behave like a random invertible function. So clearly we know that RSA encryption is invertible. Its inverse is just decryption. So that motivates us to look at the non-random properties of RSA. More specifically, we want to look at the algebraic properties of the RSA encryption function. Because if we don't look at those algebraic properties, we can prove that we will not be able to find any sort of backdoor. All right, and this leads us to our second main result of this talk. There does exist an algebraic attack, but in non-default settings. So recall that we have the algebraic relationship between the states and the output, and we can assume for this attack that the adversary gets to see some of this output. They would like to recover the states so that they can predict the future output. Now, we have this polynomial equation where we have the unknown states and the known output. And I want to point out that the unknown states here are small integers relative to the size of n. I also want to point out that the default public exponent e is 3. So this is a cubic polynomial, or a polynomial of low degree. And for those of you in the audience who are familiar with algebraic cryptanalysis, you may see a low degree polynomial equation modulo n with a small solution. And you may think this seems like the perfect example to use Coppersmith's method to solve this equation. But as it turns out, for the parameters in the ISO standard, this doesn't work. The state sizes are just not small enough for Coppersmith's method to succeed in solving this equation. But this isn't the only sort of polynomial that we can look at for Macaulay-Schnorr. What if instead of using the polynomial equation based on RSA encryption, we use the polynomial based on decryption? So if we have some non-default value of the public exponent where the corresponding private exponent is small, then we can rewrite the polynomial equation. So instead of being to the power of e, it's to the power of d. We once again have a polynomial equation that has small degree and small solutions. But unlike in the previous case, in this case, Coppersmith's method does succeed. So we do have an attack in the non-default setting where we can recover the state from the output. Now, it may seem a little bit weird that we could have a setting where we have both the default modulus found in the standard and this non-default large suspicious looking value of e. But that's not just allowed by the standard, it is explicitly recommended by the standard that this should be possible. Now, there are some other problems where it's hard to imagine a context where the choice of public exponent could be adversarially chosen and lead to this sort of attack. So there are weaknesses with this, but this attack that we've described is entirely compliant with the standard, even though there are some potential drawbacks.
All right, is my audio working? All right, so we know we're going to have to do some sort of algebraic cryptanalysis, and it seems to be hard to do with Macaulay-Schnorr. What we can do instead is we can look at a related construction that has a somewhat simpler algebraic structure that is more amenable to algebraic cryptanalysis. And by doing this, we're able to get some much more interesting backdoors. So what we're going to focus on is called the RSA-PRG. The RSA-PRG was introduced by Macaulay-Schnorr in the very same paper that introduced the construction that eventually became standardized as Macaulay-Schnorr DRBG. Like Macaulay-Schnorr, we start with some state S0, we raise it to the E mod n, we output the k least significant bits. But here, where Macaulay-Schnorr would truncate those k least significant bits and use only the remaining most significant bits as the next state, for their RSA-PRG, we just take the entire thing. So we take the whole thing, raise it to the E mod n, output the k least significant bits, take the whole thing, and so on. This gives us this really nice algebraic expression for the ith state. It's the 0th state raised to the e to the I mod n, because we're raising to the e I times. So let's go through an example. Here we have our modulus n, which is totally legit. It was generated honestly, nothing malicious about it, I pinky promise. And here we have a bunch of states and corresponding outputs. Now, why am I showing you this? It's not because I'm expecting you to verify the modular exponentiations in your head. It's because we're about to see something interesting. So far, everything looks normal. But if we go one iteration further, we see that the output has repeated. And more than just that, the entire state has repeated. States 19 and 16 are equal, which means if we keep going, states 20 and 17 will also be equal. So what's going on here? This is horrible. Pseudorandom generators should not have incredibly short cycles. Well, I lied. Sorry about that. N was actually maliciously generated. So how long should the cycles be? If the ith state is S0 to the e to the I mod n, we are working in an exponent in an exponent. We would expect cycles to have length phi of n, so that e to the I equals e to the j mod phi of n, so that state I equals state j mod n. But it turns out it's actually easy to generate parameters where the cycle length, rather than being the full phi of n, is a very small factor of phi of n. In this case, that factor is 3. So we get cycles of length 3. How is this as a backdoor? Well, the output is very clearly distinguishable from random, so we can break the security of the PRG. However, it's also very clearly distinguishable from random to absolutely everyone looking at it. I mean, the thing cycles with period 3. Anyone looking at this would know that there's something fishy going on. So this is maybe not plausible as a backdoor. However, we can take these ideas and extend them to get something that is a much more compelling backdoor. In particular, the idea that we had was there's this relation in the exponent, e to the I equals e to the j mod phi of n, that turns into a relation between states. State I equals state j mod n, a cycle. Cycles are obvious, but if we make the relation in the exponent a little more complicated, say add a few extra terms, we get a more complicated relation between the states. That does not lead to cycles, but still has structure that allows for using multivariate Coppersmith to recover the states given the outputs. We believe that if the relation is chosen with sufficient entropy, it would lead to an undiscoverable backdoor. It seems difficult to, unless you know what relation you're looking for, tell from the outputs or even the full states whether there is such a relation. So this is exciting. We have a backdoor that has very efficient parameter generation. It's efficient to exploit. It would even give a so-called no one but us style backdoor where it would only be exploitable by someone who knows the secret backdoor information. Have we found the smoking gun? Can this give a backdoor in the full MSDRBG? It seems hard because of the truncations. So in RSA-PRG, we have this nice algebraic structure where the ith state is a monomial. We can work in the exponents and move to the states. For Macaulay-Schnorr, we have this big, ugly polynomial that has exponentially many terms. And it's not even known in advance because you have to chop off the k least significant bits of output each time. So it seems very challenging to come up with anything you could do at parameter generation time that would be exploitable at, that would lead to any sort of exploitable relation between states. So further ideas will be necessary to carry this sort of thing over to Macaulay-Schnorr. So to recap, we've shown that there are no simple backdoors in Macaulay-Schnorr that only rely on being able to invert the RSA function, which does not rule out the possibility that there are backdoors that make use of the algebraic structure of RSA. We've shown that the ISO standard allows insecure choices of E, which, while not the default, would lead to insecure behavior. And we've also shown that in a closely related construction, the RSA PRG, there is a rather compelling backdoor that does not seem to carry over to MSDRBG. Now, at this point, I have a question for all of you, the audience, which is, have you heard of Macaulay-Schnorr being implemented or used in the real world? We have not been able to find any real-world implementations of this that have actually been deployed. However, at one point, people also thought this was true of dual EC, and it was only when people started looking that they realized it actually had been implemented and used in a number of real-world systems. If there is anyone in the world who would know whether some obscure cryptographic algorithm has been implemented in a real-world system, it is the crowd at RWC. So if you have ever come across Macaulay-Schnorr, if you've ever heard of anyone being asked to implement it, please come and talk to us. So where does this leave us? We have this truly fascinating open problem of Macaulay-Schnorr DRBG. It seems to have it all. It's got the intrigue of potential government backdoors. I mean, who puts a hard-coded RSA modulus into a standard? It's got a construction that's as straightforward as textbook RSA. It feels like the sort of problem you should be able to solve on a chalkboard in a weekend. It's an excuse to do algebraic cryptanalysis, and truly, how often do you get one of those? And yet, this problem has puzzled cryptographers for the last 10 years. It has nerd-sniped generations of cryptographers, and after this talk, it is my sincere hope that it has nerd-sniped all of you too. Where is the backdoor? Is there a backdoor? Was this all just a giant red herring to distract from dual EC? The answers are out there somewhere. Maybe you will find them. Our full paper is on ePrint. I highly encourage you to check it out for full details of these and other attacks. And with that, we're happy to take questions. Thank you.
So I'll use my prerogative as chair. I have a quick question about the performance of these generators compared to the AES and hash-based generators.
Mm-hmm.
Like, would there be any reasonable reason to use these generators over the hash-based or AES-based math generators, given their performance?
So the original justification for why these generators should be used is that they're based on asymmetric cryptography, so they should be based on hard computational assumptions. So sort of the justification was, even though these have poor performance benefits, they should be used because they have maybe stronger security guarantees.
As in less quantum secure?
As in based on asymmetric instead of symmetric cryptography.
Although it's worth noting that it turns out that neither dual EC nor Macaulay-Schnorr ends up with the output sizes used for Macaulay-Schnorr in the standard actually being provably reducible to well-studied computational assumptions. So
okay, let's take
not fast and also
we'll
not necessarily secure.
Yeah. So let's take one question and then we'll move on to the lightning talks.
So I've looked at this before, so it's a bit of a loaded question. In the original paper, they suggest that you could use a prime modulus. So they say, we can do this with a composite, but you probably don't need to do a composite, so you could do a prime. So the fact that this aligns with what you found, because you can use a decryption as fine. If it was prime, then you can always invert these things. Did you look at what would happen if an attacker picked a special kind of prime?
This is a great question, because it is really unclear even how you would be able to get something exploitable in the case that you have a prime modulus. I believe there is some work that has been done showing that for special types of prime, like Mersenne primes, I believe, there may be things you can do. I believe that was like Antonio Sanso, I think.
Yeah, he looked at sparse primes. So no Hemingway.
Yes, but in terms of how one would prove the security of that, I mean, it's not going to come from the RSA problem. It's unclear what sort of computational hardness assumption you would use to be able to show that this would give something secure in the case that, well, if it's prime, the factors are already known anyway.
Awesome. Yeah, this was a really, really cool talk. I think we're going to have to take the rest of the questions offline because we do want to give time for the lightning talks. So thank you so much. This is really, really good talk. Okay, and thank you to all the speakers of the session. And now we're going to move to the lightning talks. So Nigel, the floor is yours.